Can you?
Okay, good afternoon, everyone. I would like to welcome you to the English version of the presentation of the Waste Heat Recovery Simulator for the mining sector. My name is Charles Nyabeze, and I'm the Vice President of Business Development and Commercialization with the Center for Excellence in Mining Innovation. I just want to say thank you to Yann Germain, who presented the French webinar. And that French webinar will be posted on our innovation website, hopefully by tomorrow. But it gives me great pleasure to welcome our next speaker, Enrique. And just to give you a bit of an outline, for those of you who would like to ask questions, we're going to be able to unmute you during the question and answer period that will happen at the end of the presentation. And you can also type in your questions inside the chat box. A copy of this recording and also a copy of the slides are going to be made available to you after the presentation. And any questions that we are unable to answer during the presentation, those questions will be answered for you in the email that you get with the presentation. So again, I want to welcome everybody to the presentation, and I'd like to invite Enrique to please speak. Enrique, please go ahead. Thank you.
Thank you, Charles, and thank you, everybody, for coming to this presentation of the English version of the webinar. So today I'm going to be talking about the waste heat recovery simulator for the mining industry, or sector that have been developing cabinet mining that have been mainly developed by Yann Germain in the past year and a half. And today we're presenting some of the functionalities of the simulator for the industry. Okay, and we'd like to thank also SEMI, Center for Excellence in Mining Innovation, for organizing the webinar. So the contents are basically divided into 5 different parts. One is the introduction to the concept of energy heat recovery, waste heat recovery. Second part is how does the simulator work, and we will look at what are the input and output parameters of the simulator. Then we'll explore simulation example, and finally we'll just lay out some of the next steps that we're thinking of implementing in the upcoming future. So what is the problem and where's the opportunity? So the problem today, the mining industry consumes large amounts of energy, their mining operations, and a significant portion of this energy is wasted in the form of thermal energy. Okay, this residual energy may be absorbed by different pieces of the parts of the system, but then eventually they're released into the environment and lost. Okay, so where's the opportunity is to try to see some of that energy that is currently being just lost to the environment and reuse it in some of the other systems of the mine that needs that energy to actually reduce your energy consumption and fuel. And also, if fuel is displaced, reduce your greenhouse gas emission or GHG emissions. Okay, and as a result, then basically we recover energy, we reduce the mining cost, and also we set a good example for sustainable development that benefits the environment, right? So what are the bases of waste energy recovery? Basically, is to seize the energy, the waste heat energy from a system to be able to reuse it in a complementary system. Okay, so for that, we need to identify a source system, which is the one that will have the excess of energy. And we also need to identify a load system, which is the one that can benefit from that energy. And then 3 steps needs to be accounted for. Basically, first, capture the energy, the residual heat energy available in the source system, transfer that energy to the load system, and then reuse that energy at the load system. Okay. Please keep in mind that when I mention source system, in this presentation, I refer to a system that has the ability to provide that excess of energy, or that is already putting out that energy to the environment that we want to capture. And a load system is a system that can use that energy to reduce the energy consumption. So under that general assumption, the savings will always be achieved on the load systems that will profit from the energy that is recovered from the source system. Okay, and that will always need in between a transfer system to transfer that energy. Okay, as an example of that, we can see here diesel generator on the left side. So that motor, basically what it does, it uses fossil fuel to generate energy. However, only 30% of the energy, the fuel energy available for the motor turns into useful hydro energy. Okay, the remaining 70% is lost through the cooling system or through the exhaust gases, right? So the opportunity here is to capture some of that 70% of the lost heat energy and add a transport system for the heat energy, so a heat transfer network, and then add also a system to reuse that energy, for example, on a fresh air system. And that way we can use the heat that is being dissipated today from the generator to heat the fresh air to the mine site, as an example. These type of systems are already in place in some of the mines in the up north of Canada, in the region of the north. Okay. But as you can see, for these to work, you need the three components to be working simultaneously. Okay. So what are the systems, what are the equipment used for the heat transfer? As you can see in this slide, we have plate heat exchangers or coils or combustion exchangers or regular exchangers. It will depend on what you're exchanging, what kind of fluid you're exchanging, either air or water. And there's additional equipment that can be used for energy recovery. In this case, the heat pumps that use the same principle of the refrigeration machines that can allow to transfer heat from one medium to another. Then the question is to be solved basically how much energy can we transfer from a source to a load, or from a set of sources to a set of loads, okay? And how can we predict that, considering that there's different temperature profiles during the year for the environment, so the surface temperature, and also for each thermal source and each thermal loop. So how does the simulator work? Basically, it considers a number of possible sources and a number of possible loads, and an environment, let's say the temperature profile from a certain location in the country. And with those input parameters, it generates the estimate of the energy that can be transferred. And with that, you can calculate as an output the energy recovery profile and performance and the savings for GHG gases. It can also preliminary size the equipment that is going to be needed for the heat exchange. And it can also size the performance of the heat transfer network that is needed to bring the heat from the sources to the loads. Okay. What are the considerations of the program? So first, the program was built on an Excel platform. So currently it's an Excel sheet. The program was adapted to the mining sector. The energy analysis is carried out for a full year, which means that on an hourly basis. So there's over 8,700 iterations that are generated on each calculation for accounting for each one of the hours of the year. It takes into account the performance and operating temperatures, both from the source and from the load. And also, like I mentioned previously, takes into account the climate conditions of the mining site. Then, additionally, it takes into account the performance of the equipment that is going to be incorporated in the system, like that, I mean, the heat exchangers or the heat pumps, and has the ability to consider several sources and several loads. So it actually opens up the alternative to multiple combinatorial analysis here. And like I mentioned earlier, you can also use the heat pump as your part of your heat exchange alternatives. Okay. What are the current limitations of the program? First is limited to certain type of source and loads that have been programmed on it. It considers that the operation will be running 24 hours or 24/7. Okay, so it considers continuous operation of the mindset, which is kind of the expected operation pattern of the mindset. But for example, if there's a shutdown for a certain period, that will have to be considered separately in the analysis. The simulator performs this analysis according to the temperature profiles that are loaded from the Canada historical information according to the geographical positions of the site. So it might be limited in that way to the exact position temperature profile that you require. But with the ones that we have in there, I think it should be okay. And the simulator also considers constant operating conditions that input parameters that needs to be defined in the simulator. So what are the sources that are considered? There's 4 types. So there's the filtration system for processing plant. So that's type 1. Type 2 is called fluid discharge. For example, the return, the ventilation return of the mine. The type 3 are technical room cooling systems, for example, electrical rooms. And then type 4 is for bigger equipment like the generator or diesel generator, which are equipments that have their own cooling system. Okay. On the load side, there's 3 types that are considered at this point. Are the forced air heating systems for buildings. So it's basically the heating for buildings, the heating for the fresh air systems. In this case, it could be the fresh air intake of the mine, like we showed in the initial example. And type 3 will be water heating systems. In this case, can be the showers for the mine. Okay, so the way the simulator works basically is in 4 steps. So it considers a bunch of sources on one side and a number of loads on the other side, and heat transfer network in the middle. And the first step, once all the parameters have been inputted, is to model the theoretical power and temperatures from the source and the load system. So first step is to estimate what is the energy available on both sources and loads. Second step is to select which systems you want to combine with which. Okay, and then based on that selection, the first step will be to size the heat transfer network that will communicate the sources with the loads. And then the 4th step, based on that heat transfer network, is to estimate the real power that will be and energy that will be transferred between the source and the loads. Okay, which results in the estimate for energy savings and GHG savings. Okay. So now let's go into the input parameters. So for the type 1 source, which are basically the filtration systems of for processing plant, the first few parameters relate to the mass flow rate and the rock properties of that average flow rate of the plant. Then there's another set of parameters that indicate the water content or the moisture of that mix. And there's also options for water addition in the system, depending on the type of system. And finally, the last 4 parameters relate to the temperatures of the water and the ore in that in the mix. Okay, and the inlet and out. In case of the type 2, which are the hot fluid discharge systems, there's choices between whether the type of fluid is air or water. And after that, the flow has to be specified. And then the temperature before the cooling system and the temperature after the cooling system. So basically trying to identify the delta T and the T and the flow in order to estimate the energy content. And then for the source 3, the technical room cooling systems, in this case, it's a little bit different. You have choices of equipment that will be contained in the technical room, which can be transformers, variable speed drives, generators, electric motors, compressor. And then you have to input the power of each one of those equipment. And then you have to set what is the expected room temperature, and what will be the temperature difference with the ventilation system. Okay. Finally, for the source, type 4 source, which is a little bit similar to the type 3, there's a choice of 5 type of equipment that can be considered, and also 5 type of fluids considered for the cooling system of those equipment. Then you have to input the value of the power of the equipment, the temperature of the hot fluid entering the cooling system, the temperature difference between the inlet and outlet, and also the type of fluid used for the cooling system, which is one of the 5 choices that I mentioned. So now looking on the load side, for the building heating systems or centralized air systems, you have to input what is the maximum heating power required for the building, kilowatts, then supply the temperature of the building ventilation system, and then the average temperature maintained inside the building. And for the type 2 loads, which are the building heating systems, in this case it could be for example, the ventilation inlet of the mine site. You need to specify the flow for the vent system and also supply the target temperature. So for example, 3 degrees. And then the delta T will be calculated from that temperature and the surface temperature that is part of the inputs of the cell. For the type 3 load, which are the water heating systems, there's 2 options here. So the first parameters up to T1 consider showers. So you have the number of showers, the type of showers, or head, which is kind of a way to estimate. It's a way to estimate the flow that will come through the showers. You also have to input a time, the duration that they will be used, and a number of times that duration will be executed during the day, which could be associated to different shifts in the mine. And then the temperatures of the heater temperature set point and the shower water temperature. Alternatively, you might want to use the hot another process in your mine. In such case, you can use the parameters D2 and T2 to indicate what is the volume of water consumption and also the temperature that you want to use in other areas. Now, after you loaded all these parameters into the simulator, now comes the point of choosing what are the systems that you want to use to do the energy transfer. So on the source side, you have the selection whether you use each type of source or not, and then you have the choice of the NTUs, which are the number of transfer units for the heat exchanger, which represent the capacity of the heat exchanger to transfer heat, and these will be rated between 0 to 5. So you say okay, yes or no to which type of source, and then will be the NTU that you're going to be using. Okay. Then on the load side, same. You have the option of selecting which one you're going to use, yes or no. The type of energy consuming by the load. In this case, you can use any of the four in the bottom left table, which are electricity, propane, natural gas, or diesel. Then you can also decide the number of transfer units for the heat exchanger. And on the load side, you also have the additional option of using a heat pump. So you'll have a choice whether you use it or not. As I was mentioning, there is already a number of temperature profiles that have been loaded into the program, and the bottom right table shows the cities and of those temperature profiles. And as you can see, there's a number of provinces and cities that have been covered already here. And if need be, more can be added for a specific application. Okay, so after you have your loads and your charges in the system, next step is to give some input parameters for your heat transfer network, which are basically the type of glycol mixture used, the safety factor that you want to use to calculate the pressure drop of your recirculation pump, the efficiency of the pump, and the distance between the source and the load. In this case, you input the distance between the farthest source and load that will be connected to your network. And then you can select the pipe size, or you can let the simulator select the pipe size and then change that to generate additional analysis that will show later. Okay, so after you put all your inputs and you run the simulator, you'll get the following summary sheet as presented on the left side of the slide here that has 5 blocks of information. So the block A is the balance of energy available in the source, which is basically the energy that you can recover from the source, or the potential energy that you can recover from the source. B shows the potential energy that could be consumed from the loads, but also the potential for GHG emission savings. Then block C is a simplified diagram of the energy transfer between the systems that you're considering, and the climatic, it also shows the climatic temperature profile for the site, for the place that you're considering. D is the balance of the energy transfer between the selected systems, and E is assessment of the heat transfer network. Okay, so to this date, the simulator has been validated with 2 studies that we found in each group, and the results predicted by the simulator were very close to the results presented in the study. So that was a encouraging validation for us. However, we're now looking to maybe into applying these to some real case studies in the industry, which I will mention at the end. Okay, so let's go into the example now. So for the example, we used, it's based on the Eleanor mine site. So And just so you have an idea, so the team of the site is around 800 employees. The target daily production is 7,000 tons. And this is located in the James Bay in Quebec, okay? And just for clarification, we did not use current data from the mine site. We used a previous study that was done at the mine site by Handed Mining, and with certain numbers of assumptions to generate the estimations of the loads and the charges and then the heat exchange that could happen between. Okay, so the example is for illustrative purposes. It's not a part of the two validation examples that we. So here's a temperature profile, the monthly temperature profile in blue. Then there's also the water temperature profile for to the entrance of the filtering plant, and then the ore temperature profile at the plant as well. And all of these shows average values monthly. Keep in mind that the simulations are done with hourly values, not the monthly. Okay, so first thing to do is to identify what are your potential sources and loads. So in this case, there's 4 sources: the plant filtration system, the plant filtration exhaust air from the building, the processing plant exhaust air, and the electrical room local cooling. On the side of the loads, there's the 2 fresh air systems of the mine on the left bottom here, and there's also the changing rooms for the hot water and the surface garage for heating of the building. After running the first step of the simulation, we obtain the potential for energy transfer. And the first approach to this is to try to mix the systems with the higher potential for energy transfer. So in this case, plant filtration system has over 40,000 megawatt hours per year available. And the 2 fresh air systems have each one over 22 gigawatts per year and 13.5. So we'll use the one with almost 22.5 gigawatts per year. Okay. So if doing selecting only the thermal source of the plant and filtration system and the fresh air system as a load, you can estimate with an NTU of 1.25. You can estimate the simulator will estimate the energy transfer between the source and the load, which is about 64% of the energy that will result in 64% savings in the energy consumption of the load for the year. And that in terms of fuel that will be displaced, assuming that is fuel that is being used to heat the air of the inlet of the mine, it will result in almost 2 million liters of fuel displaced per year, or saved, and with a potential reduction of 3,000 tons of GHG emissions per year as well. Now, if by any reason the NTU of 1.5 turns into too much of a bigger heat exchanger for the room available, other smaller heat exchangers can be considered. Keep in mind that the bigger the NTU, the larger the NTU, the larger will be the heat exchanger, and also the more expensive it will be. So either because of room limitations or capital limitation, if there's a need to use a smaller NTU, that can also be simulated in the program. And as expected, these will generate less savings than the bigger one, as shown here. In this case, 31% of the load requirement for the year. On the left side, you can see the graph that shows how the energy savings are accumulated through the different months of the year. And as expected, because of the intake of the mine, this system will require heating mostly between January to May, and then June to September, there'll be no need for heating, and then October to December will be heating again. Okay, now in terms of the heat transfer network performance and the size of the pipe needed, the system with the following inputs here calculates the flow rate of the system and also estimates the power of the pump required to move this flow rate through the year. In this case, for a minimum diameter pipe of 150 millimeters, the power of the pump required will be 135 kilowatts with the 25% of safety factor. And the annual energy consumed by the pump will be in the range of 385 megawatts, okay, which is an additional energy that is also considered. However, if that size of pipe is not maybe the optimal, or there's questions of what is the best size for the pipe, other pipe sizes can be considered also by the program. And then there can be the argument of selecting a bigger diameter for the pipes that could potentially save energy and be cost effective. Now, if we want to, at this portion, after we did the first try with only one source and one load, now you can start adding different sources and load and combining them differently. I mean, the amount of combinations is significant depending on the amount of sources and load that are available. But just for the example that we have, there can be a significant amount of combinations. So you can start adding more systems. So for example, in this case, if we go back to the slide that shows how much energy was available at the source, which is 40 gigawatts per year, we're adding only a load of 22. In theory, there's still a significant amount, almost half of the energy is still available for transfer. So in such case, we can start considering the option of adding a new load to the system. In this case, we added the hot water. And in that case, the simulator will generate the savings. However, in this case, we also added a heat pump to the system that will help warming up the water for the showers. And in such case, the energy savings is in the range of 180 megawatt hours per year, which equates to 79% of the requirements of the load. But because you have a heat pump, you have an addition of 33 megawatt hours per year of energy that you need to run the heat pump. But as you can see, this is greatly compensated by the savings that the heat pump generate, and it also accounts for 14% of the energy needed by the heater. Okay. In case you cannot use a heat pump, you can also do the example, but only consider a heat exchanger. In the case that that heat exchanger could have an NTU of 1, the expected savings will be in the range of 19% of the requirements for the load. In this case in particular, the heat pump can prove to be very beneficial because it can greatly help to achieve the temperature difference that is required for this particular application. Okay, as shown previously, the fuel saved is also estimated, considering that the heater is run with propane, and same for the GHG emissions in terms of tons per year. Okay, on the right side, the graph shows the energy transfer between the systems if only a heat pump is considered, and it shows the monthly distribution of the energy for the year, or what happened in the case of only the heat exchanger of NTU1 will be considered. Okay. Then, as the rest of the system can be added, there's a number of associations that can be made, and this kind of opens the door to manual optimization. using the tool of the simulator. The one thing that needs to be kept in mind is that this problem of energy transfer is not only a problem of power, but also a problem of power level over time. So, like we were showing for the fresh air, there are months in the year between May to September mostly where there's no need for heat on the load system, because in this case the burners of the mine are going to be shut down because the temperature of surface is below the target temperature that the fresh air system needs. However, in the winter time, that's when you're going to really profit from having this system in place to use it. So at the time of selecting your load and your charges, there's also has to be an understanding of when those loads and those charges are going to be working for the year to find the best mix between the two. So this table here provides a number of combinations that were put together for this example. So on the left side, we have the 4 sources that we were considering. On the system load side, we have also the 4 loads that were considered. So we have 4 sources, 4 loads, and then for each line in the table, you have the additional heat transfer of the network, which is basically the number presents the megawatt hours that are required for a month to circulate to make work the heat transfer network, and if there's a heat pump, that will be included as well. And then the last 2 columns show the energy savings and the GHG emission savings as well on top. So our first example that we introduced, which made simulated the heat exchange between the plant and one of the 2 fresh air systems, had a total projected energy savings of 14,000 megawatt hours for the year. Then we can start adding new systems like we did, where we added the showers for the personnel on top of the 2 that were previously in there, and then we obtain a differential of 195 megawatt hours of savings, but we did incur with an additional energy expenditure for the heat pump. However, the balance was still positive. And you can keep adding different sources and different loads to the system to try to find what is the best combination. However, you have to keep in mind that this is only looking at the savings, not at the cost of generating these savings in terms of the infrastructure. So the best solution here, which can be the one that delivers the most energy savings, might not necessarily be the most cost-effective solution to be implemented by the mine. Okay, so if we do assume that line 4 would be the best alternative for the mine, or let's assume that's the alternative we'll keep developing. For that alternative, the system will provide preliminary sizing for the equipment that is required in terms of the heat exchangers, which have the NTU label, and also for the heat pump and some additional circulation pump that might need for the heat pump. And as I mentioned earlier, it will also give input parameter, design parameters for the pump required for the heat network or heat transfer network, but those are not displayed in this slide. And finally here, you can have also, so you'll have the total energy transfer, which in case of assuming that propane was a fuel used to generate the heating on the load side, would equate to so many liters of propane that would be displaced or saved during the year, and the same with the greenhouse gas emission reduction. And you'll have your profile over the year for for energy transfer. And there's also, you'll have the summary of the additional energy consumption, which is incurred by the heat pump, which is 17 megawatt hours, which account for 0.1% of the total energy transfer, and the heat transfer network pump, which is 208 megawatt hours, which is only 1% of the energy transfer. So as you can see, in terms of the energy that gets transferred, the additional cost of the heat pumps or the additional energy consumption of heat pumps and heat and the network, the heat transfer network pump are minimal. They're below the 2%, at least for this example. So for the next steps now, as any tool that is being developed based on the knowledge of our personnel, the next step always turns into, let's try to apply it and make a pilot of this tool with the mining industry so we can verify its usability, right? So the plan would be to compare the simulator results with actual consumption values at the mine site, and based on that, validate how good the simulator is working, and also use that to further improve the simulator based on the feedback from the mine site users. The alternative steps that could follow after that is to, like I was saying, we only have developed the energy component so far. However, we have already recognized that there is an economic component to the analysis to actually define the optimal solution for a mine site, or to try to estimate the total cost of ownership or something similar to that, that would actually give us a lead in terms of what would be the cost-effective business case, right? And because there's so many combinations that can arise from the alternatives that the program has currently, and one of the options is to try to develop an optimization function, which can be just a rule on how to incorporate the charges and loads, or some more sophisticated optimization functions. Here's my contact information, Jan, Jamin, and Charles, in case you want to ask some further questions or contact us in the future. And for me, I'm open to questions now.
Okay, thank you very much, Enrique, for that presentation. Enrique, we do have a question that it came on the chat box here, and the question is, can we buy the simulator software or pay a fee to use it?
I think the answer is yes, but they would have to contact us to figure out what is the way to do that. We haven't sold it or licensed it to anyone yet, but if the request is there, I think we can find a way to make it happen.
Okay, right. If anyone else has a question, please feel free to unmute yourself and ask the question. Thank you.
This is Andy LeMay. I'd like to pose a question, please.
Okay, go ahead.
Yes, first of all, I'm retired, so I may be a bit dated on some of the information, but my question is this. You ask any miner if it's hot underground, and they'll tell you they're dying of heat at the depth and they're freezing to death near the surface. Can this model simulate geothermal use in a mining sector to offset fuel costs? Or has it been done?
I don't think the simulator has that built in. Let me please check with Jan if that can be done in a certain way with what has been built in so far. Okay, give me a second, please.
Like just to continue to provide some parameters. Take, for instance, Creighton Mine that we have. We're down a few thousand feet there, and it's quite hot. Can we capture that heat, use it for our own purposes, and then whatever surplus we have, just to leave it go, or to even recover heat from dead mines? There's a lot of vacant mines that could possibly be used in the north as a source of thermal heat to power greenhouses, or even offset the cost of fuel in heating cities and stuff.
Okay, so what I can answer to that question is that the software as it is, the simulator, offers you the alternative to recover the heat from the return air from the mine when it reaches surface. And if that turns into be a project that is viable, that could be implemented. And there's actually, through previous of these webinars that Charles has organized, there's been some, at least one company that was offering systems of such type that would be able to use the heat recovered from the return air to be used at the fresh air, for example. That's one thing, but to the recovery of the thermal portion from the underground piece, that one I don't have an answer for that one, but if you leave your email, I will be happy to try to provide you with the information we can find.
Sure. Well, Charles knows me. If you can get a hold of me anytime, or you get it through him if he still has it.
No problem.
Okay.
I'll make a connection, Andy. Thank you.
Okay, thanks.
Awesome.
You're welcome.
Hi,
there
Enrique.
Yes.
It's Hugo here. Great presentation, by the way.
How are you?
So,
Nice
how are
to hear
you?
from you.
Yeah, no, so just to answer Andy's questions there, I mean, I had made some analysis a bit on that to try to see if it was, worth it to take the heat from the depth, right, that have better quality there. Yeah, so, I mean, and really there, it's the problem that it's not feasible because of all the piping that was required to be done there to go get that heat with of higher temperature there for the underground. So it was more feasible definitely to get it from the exhaust there on surface. Not sure if that answers your question, Andy.
Well, yeah, thank you very much. I'm very aware of that, but there's been so little thought or work done on the thermal capacity of our ore and the amount of heat that we can extract out of the last survey I could talk to, or the last report I could talk to, was Gameshis from the University of British Columbia, who tried to quantify some of the potential availability of heat that can be used, and especially in abandoned mines, where if we can use these for those, like just putting a thermal pipe into it, like they have in Nova Scotia, and recover the heat for the municipality. Like, for instance, one of the items, I know I'm talking a little extra here, but one of the items here for Sudbury, we just took down a mine. Did anyone think of putting in geothermal pipes to recover heat down there? There's enough heat underground there to have been able to power, not power, but to keep a greenhouse working year round, and with other renewable energy like solar and wind for the electricity, you would have a perpetual greenhouse to provide fruits and vegetables up here, which can be very well used up north in some of our northern mines in James Bay. So basically, I guess what I'm really trying to say to everyone here is, great, I love the simulator. Let's see what it can do for people, not only within the company, but also outside the company. And as for the mining company, is how much fuel oil can you save by not having to buy a lot of the heat and cooling that you have in your buildings now that is just sitting residentially in the ground at your place? You have the hole already. All you need in the mine, all you need is a heat exchanger underground to bring that heat back up to surface. This is what I'm asking, can this simulator do something like that? Taking the heat from the rock, not the air.
So at this point, I don't believe we can do that, Andy.
Yes.
Only the portion that I mentioned on the return, and that Hugo, his master thesis on that a number of years ago. That's that I'm aware of. But I'll follow up with Jan to see. He has worked on some stuff like that before, so I'll see if some of that could be of interest or not. You have to keep in mind that when you bring something from a depth of the ones that Creighton has, there's more to be involved in the picture than just the heat that you can recover at 2.5 kilometers down.
Yeah.
In terms of that's going to look when it gets back to surface, you know.
Well, yeah, well, thank you very much, Enrique. I understand that I'm putting everybody on the spot, but as Charles knows, I've been pushing geothermal for years, and just to say we need to expand our mind to include much more than what we're looking at. This is a fantastic simulator. I wish I would have had it 12 years ago, but it's a good beginning. But let's use it for all the heat that's in the mine, for all the energy that we can get out of a mine, that and also to offset some of the energy that we're using for not only production but also for everything that we do to mine, which does include a lot of the communities and stuff.
That's true. That's true. That's true. And I think, and you're right. I think, even with the big movement happening right now on things like, renewables and ESG, I think those opportunities will become more and more apparent. Okay, folks, does anyone else have a question they'd like to ask? Just please unmute yourself to ask a question or type it in the chat box. Thank you.
So I guess, Enrique, just the question I had there is with respect to the, you were talking about the equipment sizing there for the heat exchangers. Can you explain a bit more in detail what we can get out of this for the sizing of the heat exchangers?
Yes. So from what Charles was presenting in the previous, actually the same question came out in the previous presentation in French, is that the NTUs can be related to the charts of the silencers that the manufacturers can provide you. So based on the NTUs and the parameters that you need for that heat exchanger, the provider will be able to estimate the size and the cost of such heat exchangers that you need for the application.
Okay, you'll even have a cost.
Well, I'm not including the cost here, but I'm saying that this is a preliminary sizing that is an output of the simulator right now, and that can be used for the final year according to different suppliers, and also then the cost for that sizing, right?
So you're going to have sort of overall specs for that.
Yeah, well, or some inputs to a spec that the supplier can then help you to finalize.
Oh, okay. Okay, got it. Thanks.
This is Andy again. Excuse me. This is a technical one on the simulator itself. I noted when you were talking about loads, I missed out on it. Have you considered energy storage as part of a load for this?
We did initially, but we haven't built it into the simulator yet. But it was one of the things we were talking about. And you mentioned that you come from Creighton. I actually had the great opportunity to work there too. So I'm also familiar with the natural heat exchanger that they have. So we have another project with that heat exchange system. So we were thinking about maybe ways to add that into the simulator, either as just a storage, some kind of a storage, or the other seasonal storage that is already present at Creighton Mine. And those are avenues for development in the future. They're not currently developed in the simulator that we have.
Okay, thank you.
Okay, there is a question here from Albert. Enrique, the question is, what are you looking for a mine site to verify the simulator? What will you require to do? What will you require to do that?
Can you repeat that, Charles?
Yeah.
What are the requirements for use these in the mining?
The question is, are you looking for a mining site to verify the simulator?
Yes.
I think that is yes. Okay. And then the other question is, what will you require to do that? I guess the question is, what will you require from that company in order for you to validate the simulator with the mine site?
So the parameters that we have in there will be the first requirement, and then of course find an arrangement so we can make that happen, right? So if whoever is interested, please, share your email or take my email from the contact there, and let's start the conversation.
Okay, folks, anyone else has a question, please feel free to ask. You can unmute yourself to ask the question. Okay, Enrique, seeing that we've got about 4 minutes to go and I don't see any questions coming from anyone. Enrique, would you like maybe just to say some closing remarks before we end the call?
I'm thinking, okay, Charles. I mean, I'd like to thank everybody for attending these 2 webinars and for giving us the opportunity to present the work that we have been developing at Canyon Mining for the last 1.5 years on the waste heat simulator. And please, we all want to bring these to a mine site and use it with the data from a mine site. So if you're interested in doing that, please get in contact with us so we can find a way to materialize that and hopefully bring some value to your mindset in terms of the potential waste heat recovery that can be achieved, and also to improve the simulator that can hopefully make it available to mining industry in a more extensive way. Thank you.
Excellent. Okay, everybody, thank you for joining us on the call. Remember, there will be a link coming into your inbox for you to rewatch this presentation, and also you get a copy of the slides as well. Thank you again for your participation. Have a wonderful day, everyone.
Thanks, Enrique.
Thank you.
Thank you. Thanks, everybody.
Bye.
Bye.